Good afternoon, everyone. My name is Veselova Svetlana, and I'm from National Research Nuclear University, MIFI, Moscow. So the name of my topic is numerical simulation of the second generation HTS tapes under the pulsed magnetic field impact. So the motivation of our work. One of the practical applications of the high temperature superconductors is levitation technologies such as levitation transport, magnetic bearing, etc. As superconducting elements, as rule, bulk materials are used. But the bulk materials have some disadvantages. For example, low mechanical strength, relativity low critical current, density, low superconducting properties, and exposed by water vapor. Moreover, there is significant difficulty in optimizing on size and shape of HTS bulks. An excellent alternative for using of bulk superconductors in levitation systems and another energy systems are modern HTS tapes in the form of stacks. Rarely coated conductors have good mechanical properties, high values of critical current, and it is easy to construct the stacks of different shape and size. In previous researches, the HTS tape stacks can trap large magnetic fields, so such stack may be used in levitation system or various application and as a trap flux magnets. Superconducting windings are effectively used in HTS motors and generators. However, their work often requires the pre-magnetization of the superconductor and then periodic replenishment of the magnetic field. Because at nitrogen temperatures, there is a thermal relaxation of the trapped magnetic flux. The magnetization of the superconductor can be done with different ways. In particular, superconducting or resistive magnet can be used. However, such systems are too large and complicated to be assembled directly into practical devices. As an alternative, some techniques based on pumping magnet field into a superconductor can be used. The aim of present work is searching for the possibility of magnetizing HTS tapes or stack of tapes by a small source of magnetic field. The calculation results. To study the process of magnetic pumping, we consider it the following model situation. We took a second generation HTS tape with dimensions of 12 to 12 millimeters as a sample for flux pumping. A small copper coil are used as a source of external local magnetic field. Magnetization was performed by multiply pulses at the fixed position of the coil. Evidently, magnetizing pulses followed one by one without interruption. We also ignored the process of slow change in the magnetic moment on the sample between pulses. To calculate the density of induced current HTS tape fragment, we used an adapted critical state model for a real sample. The critical current density dependence, the magnetic field, is determined by the two exponential approximation. Problem of the mathematical calculation of the current distribution in superconducting tape and details of a numerical method are presented in its articles as you can see later. To estimate the magnetization of the sample, we set the maximum volume of the magnetization M0. which could be obtained from the Bean model. This value was the maximum of practically unattainable due to the dependence of the critical current of the magnet field. It also corresponded to the state of complete penetration of the flux into the superconductor. However, when the sample was magnetized by a homogeneous external field, the value of the residual magnetic moment could be close to the value of M0. Indeed, our calculations for magnetization by a homogeneous magnetic field with an amplitude B max 0.126 Tesla after the first magnetization period T to T0 equal to get the magnetic moment M equal 0.899 M0 988. Subsequent periods of magnetization T to T0 4, 6, 8, etc. Practically did not change that value. This graph shows the distribution of the density of the induced currents. The magnetization of HTS tape was calculated by a local homogeneous magnetic field with different amplitudes pumping. Dependent on the amplitude of the applied field, fundamentally different results of magnetic pumping were obtained. So if the Bmax value is small, then the sample's magnetization is strictly periodic, and its period considered with the period of the external field. And the end of each magnetization cycle, 2, 4, 6, etc., the compute flux equaled 0. The magnetic field was not pumped. When Bmax was increasing, the magnetization function became periodic, the field was pumped. However, if the Bmax value is below a certain threshold value, the residual magnetization will be much less than M0. In addition, the sign of residual magnetization is opposite to the sign of induction of an external magnetic field. A figure shows the dependence of the magnetization, as you can see. If the threshold is exceeded, the volume of the residual magnetization falls, then it takes negative values, and after it goes into a steady state periodic process. The end of each pumping cycle in this steady state process, the magnetization approach to the value. The sign of residual magnetization coincides with the sign of introduction of the external magnetic field. It shows the time dependence of the magnetization. As the amplitude of the external field increases to the value Bmax to mu0 is equal 0.8 times 105 ampere to meter. The approach to the maximum value of the magnetization becomes faster. The dynamics of the distribution of currents in the sample during pumping is shown. Next slide corresponds the instant to the T to T0 equal 1. When the external magnetic field first reaches its maximum value. It can be seen in this figure that the induced current occupy only a part of the sample and are considered mainly in the region localization of the external field. A figure corresponds the instant t to t0 is 2 when the external magnetic field vanishes, the first pumping period ends. The number of current lines indicate the value of two-dimensional density of the magnetic moment. This figure shows an increase in the magnetic moment density in the certain part of the time. This increase is due EMF arising the sample under the action of the varying external magnetic field in the time interval t to t0 between 1 and 2. After exposure to 4 pumping periods, the magnetic moment density at the center of the sample increased markedly. With further pumping, the magnetic moment density becomes positive and the distribution of currents practically does not differ from the source by a uniform field. An increase in the amplitude of the external field up to the value Bmax accelerates the magnetization reaching the limited mode. However, with a further increase in the Bmax amplitude, magnetic pumping becomes ineffective. After several cycles, the magnetization can reach the maximum value, but it eventually destroys the achieved magnetization due to remagnetization and the formation of the complex current configuration. It's a black line on a graph. At the same time, Bmax amplitude exceeds more the value of Bmax. The stochasticity of the residual magnetic moment is more stronger after each period. The dependence of maximum forces on number of tapes in cases both vertical and horizontal forces measurement can be extracted from the force displacement curves for various number of tapes. We can see that the dependence of maximum repulsive force and maximum lateral force on number elements in the stack have a similar behavior. It is clearly seen that both forces grow with the increase in the number of elements in the stack. Also, dependents have a tendency to saturation. Together with forces, data represent a dependency of Fremont induction, which was measured by a Hall sensor on the surface stack. Experiment details. To verify the results of calculations, experimental study of magnetic pumping of the HTS tape by the magnetic pump method were carried out. An experimental setup was created based on a free coordinate displacement system. The research was performed in 2 modes. In the first case, a pulsed copper coil diameter 10 millimeters was used as a source of local and homogeneous magnetic field. The magnetic field was 22 millitesla and the current was 9 ampere. To reduce the area of local magnetization, concentrator with a diameter of 3 millimeters is fixed at the end of the coil. The duration of the current pulse was 1 second. The coil was located in the center of the sample. The field concentrated at the surface on the tape. Magnetization was performed by successive switching on and off of the current in the coil. In the second case, a permanent magnet with dimensions of 1.5 millimeters was used for magnetic pumping. The field on the surface of the magnet was 389.7 millitesla. So pumping in this unsymmetric case occurred efficiently because the current loops that were induced during each cycle of magnet supply and removal from the superconductor were uncompensated. To determine the localization of sample magnetization, the local distribution of the trapped magnetic flux was measured after each cycle of field increase using whole magnetometry. The spatial distribution of the trapped magnetic flux of the sample was measured in advance of the single magnetization in the field of 0.45 Tesla.
Sorry, 2 minutes. 2 minutes.
Okay, I move on to the conclusion. So to summarize, we can say that one of the basis of theoretical calculations and experimental studies, it was shown that source of local gradient magnetic field can be used to magnetize the second generation HTS tapes. Three main modes of magnetic pumping can be distinguished depending on the amplitude of external magnetic field. At low amplitudes, the field is not pumped and accelerated associated with the input and output of the flow appear at each pumping cycle. In medium fields, magnetic pump is observed and reaches 94% of the maximum trapped magnetic field with a complete magnetization in a constant uniform field. However, it is achieved in fields of the order of 10 times lower than in case of uniform field. At high fields, the magnetic pumping is stochastic. The amplitude of the trapped field is also depends of the pumping method. In particular, it is shown that with the central method of localizing the gradient field, the amplitude of the trapped field turns out to be 30%, greater than under the same conditions, and pumping from the edge of the sample. In addition, in the case of central pumping, a greater magnetic flux gradient appears. Thank you so much.
Okay, just a small question, please. It's a pity we cannot finish to see all the results, but you have compared theoretical results and experimental results.
Yeah.
They agree or you have find differences?
Yeah, that's experimental results. And we can see that the green line shown that sample have no magnetization at low fields like 9 millitesla. The second line is red, show the slow sample magnetization. It's 17 millitesla, and the last line shown faster sample magnetization, faster and stability, that is 39 millitesla, and we can see that it looks like our model, but in real life.
Okay, thank you very much. Thank you again,
Thank you.
our presenter.